to our first weather and climate class via online. As the t-shirt today says, we're all in this for the first time. This is not going to be pretty, but hopefully we'll get everything through, and heck, I might even improve. But anyway, okay. So we're going to be starting out today with a little bit of review, talking about the adiabatic heating and cooling rates that we were talking about before spring break and before we got invaded by Corona and things like this. Now, probably what things that you've noticed going on outside is that the weather's been really not knowing what it wants to do. We've had warm and sunny and warm and rainy and warm and cold and rainy like it was yesterday. I mean, it got back down into the 40s. It's cool today. It's rainy. It's supposed to be back up in the 70s and warm. So we're finally going to be getting around to explain to why that is and why that is actually normal, and why it's also wreaking havoc with everybody's sinuses. You'll see that I will probably be either coughing or sniffling. It's not coronavirus, I swear. It's just my regular seasonal allergies. Same with everybody in my household. So it's okay. I don't have a fever, but it wouldn't matter because you can't catch it over video. Anyway, okay, so what we're going to do, I'm going to look over the lab exercises that you guys did. So have your lab books handy. Make sure you go get those. And so we were playing with the adiabatic cooling rates. And the adiabatic rates have to do with when air is forced to rise, all right? Like when it hits a mountain. So that's the one that we use as our most visual example. The air is going to cool off much quicker than it does. So if I can get this lined up, scoot in so you guys can see it. All right, so here was the first lab work that you guys had done here in exercise H of your lab book. All right, and so we know as you go up into the atmosphere, the air is going to cool down. And we know we've got that regular rate. This is talking about air that's not moving and how it cooled off at the different rates. But we have now learned that if air is being forced to rise, all right, like it is when it's hitting the mountain and going up, it's going to be cooling off at a much faster rate. And so you can compare the differences here between the air that's moving along the side of the mountain, where it cooled off to 69 degrees, versus the warmer 73 degrees over here. Of course, the wind's still blowing and it's being forced up over the mountain. All right, so it cooled off to 55 degrees up here versus the 64 degrees out here in the air that is not moving. This is going to be colder, therefore it's going to be denser. So it's going to, do like any heavy thing's going to do. It's going to roll down the hill. All right, and it's going to warm up at that adiabatic rate. So it's going to end up at the same, temperature it was over here as it was over here. Where some things changed was when we actually cooled off to, all right, the dew point. So in this example, the air was more humid. There was more moisture, water vapor in the air. And when it rose up to that 69 degrees, that happened to be the dew point. Remember, the dew point is just the temperature at which the capacity of the air shrinks. All right, can't hold as much water, and so we actually become completely full and a little bit spills over. And the water vapor condenses into liquid water and we get clouds. All right, so 69 degrees in this case happened to be the dew point, and that's where we got clouds right at this level. In this case, it was a 3,000 foot level. All right, now because of that, all right, the rate of cooling is going to slow down a little bit. It's still going to cool off as it continues to rise. It's just not going to cool off as fast. That's due to the latent heat of condensation. We remembered that converting from water vapor down into liquid water. Doesn't require as much energy at all. And so extra energy is just dumped out into the atmosphere. So it's like, again, turning a space heater on as you're cooling off. You're still going to cool off as you rise up, but not as fast. So up here at the top, instead of being that 55 degrees, we're now only 61 degrees. All right. It is still it's colder than the surrounding air. This was 64 degrees. All right. So it's still going to sink when we go back over here. But let's go back looking at these clouds. As it's rising, all right, the temperature is lowering, which means that the capacity continues to shrink and squeeze out water the whole time. That's why we have clouds for the entire distance that goes up here. So we keep, as we cool off, we continue to hit the new dew points. Dew point, dew point, dew point, dew point. Okay? And we had some questions where I was asking, what was the relative humidity at these two levels? All right? Because we got clouds, that automatically means we are completely at capacity. The air is saturated. In other words, we have 100% relative humidity. But then they asked how much, what was the question was, what was the water vapor capacity? All right, and that was just, we used that chart back at the very beginning of this exercise. This is exercise H. All right, and we looked up on the chart as in what is the capacity at 69 degrees. And we found out that it was 7.8 grains per cubic foot. All right, so that's the volume of water that can be held in that little cubic foot of air. All right, now, and then it asked the question was, well, how much water do we actually have? And that's a very easy question. It can hold 7.8 grams, and we're completely full. So that means we've got 7.8 grams of water. That's what the volume is. Up here at the top, we still have 100% relative humidity because there's still clouds. Now, the capacity is going to be less, but again, we used the chart back on H1 to see what the capacity was at 61 degrees, and it was about 5.9 grains per cubic foot, somewhere around there. And again, so they ask, well, what's the capacity? 5.9 grains per cubic foot. And what is the, how much water do we actually have? What's the volume? Well, it's 5.9 grains per cubic foot, because again, we're still 100% full, 100% relative humidity. All right, but this time, since we're starting out with slightly warmer temperatures than we did in the last example, okay, now it's still going to heat up very quickly as it comes down, but it started out warmer to begin with, and so when it ends up over here, instead of being 80 degrees, it's, close to 86 degrees. So it's much warmer. All right, that extra heat came from the latent heat of condensation, the heat that was dumped out over here into the air during the condensing process. And we remember that we talked about, of course, we know this air that's descending is going to be drier, okay, just like a sponge that was wet, completely wet. We squeezed out all that water, and so the sponge is drier and has a lot of, capacity now as it's warming up, and it's got lots of capability of evaporating more water. So we call it a dry air. All right, and so we remember when this happens on a regular basis, we call those föhn winds, or the Chinook as we call them here in the US. All right, but it was forming that. All right, so hopefully you guys will remember this type of stuff. Now, carrying on at this same topic here, let me set this aside over here. All right, a couple of terms I need to get you guys into. Here we go. All right, term stable versus unstable air, okay? Air that is, I'll figure this out here in a minute, guys. All right, Air that is stable means that it is either the same temperature as the surrounding air or it's cooler. Point is, it's either going to be staying in the same location or it's going to be sinking. That's stable air, all right? So it's usually cooler air. Air that is unstable, all right, means that it's warmer than the surrounding air, which means it's less dense, which means it's going to, of course, rise up. And whenever we're talking about clouds forming and then eventually precipitation, they talk about unstable air. You'll hear the weathermen referring to that about, whenever you've got unstable air, that means you have the potential for clouds to form and then possibly precipitation. All right, so stable versus unstable. Unstable is air that's rising. All right, just means it's rising. Stable air means it's sinking. All right, so in a high pressure situation, we know we have colder air. So high pressure usually means the air is stable. Unstable air, low pressure systems means that the air is rising, right? So stable versus unstable air. All right, well, we talked about clouds in our lab. So we need to learn the different cloud types. Now, there's a cajillion nitpicky cloud types, but they all can boil down to some very, very basic cloud types. And let's see, maybe it will be easier for me if I hold it up on this. All right, so here we go. All right, we have, all right, first off, we're going to start with height. There are different layers that are found here in the atmosphere. Do not worry about the actual amounts. I don't even know them by heart or anything like that. So you guys don't have to worry about that. All right. But first we're going to talk about these guys right up here. These are the cirrus clouds. The word cirrus means they're way high up, way high up there in the atmosphere. These are the real wispy looking clouds that you can sometimes see way high up. You can see through them. They're sometimes called mare's tails, talking about a horse, a female horse, and her, hair tail, that runs out and looks real wispy as they're running and things like this. But those are called cirrus clouds, all right? FYI, these are actually ice crystals because we're going to be super high up within the troposphere. Temperatures are going to be below freezing, so, they're going to have instead of condensing, there's actually going to be sublimation going on. So cirrus clouds are going to be ice crystals, all right? A little farther down, we can also, of course, get clouds. Now, the clouds that we have outside today, this is Sunday afternoon, and we've had the past few days, they look like a blanket. They cover the sky from horizon to horizon, and these are called stratus clouds, all right? So when you can't pick out an individual cloud and it's just all gray, we talk about an overcast day. It's going to be referring to stratus clouds. Now, yesterday afternoon, it had cleared up. I'm talking about this past Saturday. And there were still some clouds out there, but they're little poofy clouds. They look like little cotton balls or bunny tail or however you want to describe it. But those individual little poofy clouds are called cumulus clouds. All right, you can have more than one. They're also called fair weather clouds because they'll, show up on nice days. You still have a few little pokey clouds and stuff there up there. Now, this big cloud we have over on the side, the one looks like Marge Simpson's hairstyle over here. Very, very vertical type structure, but it's still fluffy. All right. This is called a cumulonimbus. These are the thunderheads. These are the thunderstorms that do form, and they're famous. What distinguishes them is, again, there's extreme vertical height. These are built in very unstable air. Now, keep in mind, to have any type of cloud, that means you have to have adiabatic cooling going on. You have to have air that's being forced to rise. All right? But when it's, there's a lot of energy out there, that's when you can get the cumulonimbus that go on. Now, another term that you can add to this, so let me add it real quick, is referring to, it's strictly a height term. All right, so just like cirrus, Sometimes you'll see the word cirro. There we go. Is referring to, again, height. The term alto right here, all right, that means middle. It means it's not the lowest, it's not the highest, it's right here in the middle. So we can attach the term alto to any of these. We might have some alto cirrus that are, you know, kind of fall in this area up here, aren't in the highest. Or we might have alto stratus if the stratus clouds are a little bit higher. So let me draw some of those in for you. All right, so there we have the alto stratus. All right, still the same blanket layered looking type, but they're higher up. All right, so you can, again, just tack on that little prefix to any of these terms to goes on. Now, there's another prefix that we use, tack on. We've seen it already over here with cumulonimbus. It's this word nimbus or nimbo. That means rain, all right, precipitation. So you can attach that to other words to let you know, hey, it means it's, you know, it's got rain and it's going to have precipitation. So down here we have stratus. All we have to do is add the word nimbostratus. All right, to mean it's a rain cloud. All right, so stratus is just the clouds, but if there's rain coming out of it, it means nimbostratus. All right, it means, so that word nimbo just means rain. So whenever you see that attached to something, you know you've got precipitation coming out of that as well. All right, so there in your lab book, in your textbooks, you can Google all these types of clouds to see actual examples of them in real life, but they're, I mean, they're very easy to understand. Now, sometimes you'll get things that are a little bit of one, kind of little hybrids. It's very easy to get kind of like cumulostratus, where you would have possibly a bunch of, let me see, they're still cumulus clouds. They still got breaks between them, but they kind of spread out like this. Combination of that. Same thing with cumulocirrus, or, you know, you can have alto cumulus or whatever like this. So combinations of those. I'm not going to be actually, you know, showing you any actual photographs on your test when it comes around. It's going to be these really cheesy drawings that I've got here. So, but again, very easy to identify. So when you guys are out looking at clouds, which you can easily do just about any day that goes on, you can, you know, decide, is it a cumulonimbus? Is it a cumulus? You see those a lot. If you see the nimbostratus and stuff like this. Now keep in mind, if you have a cumulonimbus cloud right on top of you, and especially here in the Mid-South, where we don't have a whole lot of wide open spaces, you're not going to be able to see the edges of it. You know, you just know that it's a thunderstorm that's going on. But you can easily spot these from distances. You can see them off, you know, if you look across the river, or, you know, just off into the horizon, you can see these big building clouds that show up and things like this. All right, so for a minute, let's talk about all the different ways you can get your unstable air. You can get your adiabatic cooling going on. Now, we've already talked about the orographic type, which occurs. Hold on just a minute. Where did I? All right, I forgot to write these down, so I'll just have to tell you. All right, so you've got, you know, you've got the orographic, which is the ones with the mountain. All right, so those can make rain. If we have a low pressure system that comes through, basically a cyclone, all right, we know that the air is rising underneath low pressure. And so, yeah, you're going to get clouds associated with that as well. We're going to be talking about that in detail coming up next. Now, you can also just get your good old, plain old convective heating. This is what happens on a nice, clear day, all right? Sun shines down, warms up the ground, and the heat starts to rise. and you're going to start getting little poofy cumulus clouds that show up. Just plain old convective heating. All right. This is why, especially in the summer months, once it starts to warm up, in the morning, you may have totally clear skies. It's beautiful. All right. But we know if it's very humid here in the Mid-South, by, around noontime, you start getting a few little poofy clouds show up, and then by later afternoon, it's more partly cloudy, quite a lot of little poofy clouds, and some of those may even build into thunderstorms. We talk about those, just scattered afternoon thunderstorms, or garden variety thunderstorms and things like this. All right, that's just from convective heating. And that's a good way of figuring out how muggy is it outside, how high is the relative humidity. If it's 3 o'clock in the afternoon and the sky is still perfectly clear and there aren't any clouds at all, by George, relative humidity is going to be really low out there. All right. If you've already got poofy clouds forming, pretty early in the morning, then it's going to be a really, really muggy day out there, because the more absolute humidity in the air, means the higher the relative humidity, and the better chance you have of clouds being able to be formed. All right. Also, an FYI, a lot of the cirrus clouds that we see are actually man-made, in the sense of they are the condensation trails of the contrails. That's what condensation trail stands for. Contrails is condensation from airplanes that go through. They're flying up there. It's a combination of, they are act as a nuclei, condensation nuclei as well, but they've also got water vapor that they expel from their engines, which will increase the relative humidity and cause condensation to occur. And then as those guys spread out, they get turned into the real wispy type of thing. So actually, the amount of cirrus clouds that we have, many of them are actually made by airplanes. They're not chemtrails, all right? It's strictly water vapor. It's no big whoop, all right? They do not poison you or anything like this. But you can see those, they start out straight and then they start to kind of lose shape and dissipate out. But you can see those on some days that are pretty cool, all right? And especially on days where the air is very stable, they will hang around for a much longer time. All right. So, but yeah, that's how they're up there, because a lot of times because of the airplanes that are flying up there. All right. So that's your clouds. One of your assignments, just observe the clouds. Pick out the different kinds of clouds. Oh, that's a cumulus. Oh, that's a stratus. Oh, that's kind of a combo. That must be, is it real low to the sky? Is it, kind of up, or is it way up there? So those are easy things to do. All right, so let's talk about precipitation. Not every cloud will rain or have precipitation that comes of it. And of course, you don't always get clouds. Whenever you've got adiabatic cooling going on, it doesn't necessarily mean you're gonna get clouds forming. It's going to be dependent on how much the absolute humidity is, what the relative humidity is, what the capacity is, what the dew point is, and, so just because you have adiabatic cooling doesn't mean you'll automatically get clouds. But when you do, it's a possibility that you can get precipitation. Now, what is precipitation? All right, for my class specifically, all right, precipitation is the wet stuff that falls out of clouds. So it's not the cloud itself. It's not going to be dew. It's not going to be frost. Those are forms of condensation. I'm wanting to make this point for this class that, again, condensation, remember, is in place. It has to occur on a solid object. It's in place. But if it's falling out of a cloud, that's what we're going to call as precipitation. All right? So basically what happens, let me show these signs up here, all right? Precipitation is when the condensation gets too heavy to defy gravity, and it's basically being held up by those rising air currents, all right, that lifting that's going on. But if it gets too heavy to be held up by that, it's gonna fall, all right? And that's what precipitation is. Now, your basic raindrop is made up of 1,000,000 cloud droplets. If you've ever driven through, been in an airplane and driven through a cloud, you can't actually see a cloud. Of course, if you walked around in fog, that's the same thing. It's just condensation. Those itty bitty little condensation drops are pretty much microscopic, all right? They just make a little haze type of thing that goes on, all right? But water likes to stick to water, all right? It's a surface tension. And this is why you actually use soap. By the way, we're all using a whole lot of soap. Soap breaks up the surface tension, the tendency of water to stick to water. And when you use soap on your hands, that breaks up that surface tension. So the water, instead of sticking to the water, will stick to the germs on your hands and wash them off. That's where you use soap. But it's also, of course, the surface tension, water sticking to water, that, water gravitates to water. And that's why, it can be fairly easy to get 1,000,000 of these little itty bitty drops sticking to there and growing up. Now, your basic raindrops themselves are not very big at all. They range in size from 0.1 to about 1/4 inch. And this is actually, give you an idea, put my finger here, all right? And here's my actual little finger. I figured out that my little pinky fingernail is about the same size as 1/4 inch raindrop, all right? But it can be smaller. So, it can be teeny tiny little points here as well. But that's what the raindrops. Now, we do have different types of precipitation. We know it's all water in some version, all right? But there's different names depending on how it's formed and whether it's liquid or solid as it goes on. So, of course, we got rain, which is the liquid. Some other names, when it's usually the itty bitty little ones here, it's known as drizzle. Sometimes we call it mist. Those are all the same terms. That means the liquid state of, the condensation that's falling out of the sky. Okay. And we snow. Okay. We haven't really gotten much of that this year here in the Mid-South. This is made from water vapor that sublimates. Okay, so it skips the liquid stage. It goes straight from water vapor into the, let's call it fluffy. It's actually a crystal layer. It's the same thing as frost that occurs. All right, we know frost is just, when the dew point is below the freezing temperature, you get the frost, sublimation occurs, and again, it's fluffy as opposed to an out and out frozen water drop. Now that happens, all right? Let me back up here. Let me back up to snow. Just FYI, like I said, snow's fluffy. It's made up, little snowflakes, which are crystals. You can, look up what they look like if you would like. When it falls, again, it's like little bits of styrofoam, so to speak. There's a lot of air trapped within it. And so as a general rule of thumb, a foot of snow actually only equals about 1 inch of rain. So when we get those dustings of snow, that's not even a 1/4 inch of snow, that's a tiny amount of rainfall that actually comes down. If you want to measure the liquid water a bit. So, and this is just an average type of deal that goes on. All right, so sleet. Now, we get sleet here in the Mid-South. Sleet hurts when it hits you. If you've ever been out when it's coming down, and it makes a lovely sound on your windshield. I remember, being out driving around and realizing that the raindrops were sounding a little crunchy. It's like, it's sleeting out there. This is literally frozen rain. So it starts out as liquid, and then it falls through a layer of air that is below the freezing temperature, and that liquid water drop literally freezes into a very hard pellet. All right? So it's kind of like ice cubes, but on the smaller side. All right, that form. All right. Hail. All right. This is similar to sleet. It is a frozen and layered droplet of water. It is formed in thunderstorms. It is not a wintertime precipitation. It's usually associated in summertime when we see the big thunderstorms. We will talk about hail in a lot more detail after test 2 when we get into the severe weather section that we're going to be taught. Why can I not do this? Here we go. All right. But hail is considered a form of precip. All right. Now, also something that we dread and that we do get here in the Mid-South is this thing that we call freezing rain. Everybody else on the planet calls this glaze. All right. But we call it freezing rain. And what this is a very special situation. This is where you have liquid water, plain old rain, but it's super cooled. All right. That means that it's below the freezing temperature, but it has not turned solid yet. Right. It's very unstable. And the minute it hits anything solid, that liquid water comes down, hits the ground, the telephone wire, your car, whatever, your house, tree branches, and immediately, it spreads out because it's water, splashes over, but then it freezes. And the trouble with freezing rain, what makes it so bad, is that it will completely coat whatever it lands on, be it the road, be it your car, be it tree branches. So imagine the difference. I'm going to use, my husband's going to kill me. I have some jelly beans here. My husband's, well, if I can get it open. This is good. We're going to pretend this is a little sheet of, or pieces of sleet. Because sleet is, of course, individual pieces of, frozen pellets of water. Yeah, all right? So it can pile up very good, and it's individual, and it can, it's only going to be on the very top, and then, any extra, just like is happening here, it's going to fall off. All right. But the glaze is just like if you pour glaze on a donut, all right? Is it spreads out and then it hardens. And it cover all the way around. It can even go underneath at times. And then it can build up and build up and build up. And that's what's so bad about that freezing style rain. As more comes down, it spreads up, it builds up. Ice is very heavy, and that's why you can bring down telephone wires and break tree branches and all things like this. This is why it's so bad when we get a really bad freezing rain type deal. That's why the wires come down, the power lines come down, and you get stuck without electricity, which is really bad when it's really cold outside. We don't like that. Whereas if it's just sleet, all right, that's just, a little bit's going to fall off, but most of that sleet's going to fall off, especially the power lines, because they can't stay on. And now I've got jelly beans all over my floor here. Oh well. All right. So, yeah, glaze is bad. We do not mess with the glaze or the freezing rain. All right. So hopefully you guys, there we go. All right. So again, you can look these up and stuff like this, but make sure you know the difference between these and how they're formed. Now, a lot of times, what we get as rain, especially in the wintertime, it actually starts out as snow way up higher in the atmosphere. And by the time the snow falls, temperatures have warmed up as you get closer to the surface. And so the snow literally melts and just turns into regular raindrops. So that's kind of cool. This is often where will happen if you are in a mountainous area where it can be snowing at the top of the mountain, but raining down at the foot of the mountain. I've actually experienced that. Over in the Smoky Mountains, they've gone whitewater rafting. I guess it was in the April one time. And we went up in the mountains and it was completely snow covered because they'd had a storm that had come through the night before. And there was like a foot of snow up on the top of the mountain. We were not dressed for that or anything like this. And then by the time we, took a 5-minute drive further on down, it was just, everything was wet, and it was, you could tell it had just rained. It was no big whoop that goes on. All right. So that's precipitation. All right. Let me check my notes. We talked about that. All right. So conditions causing precip. Let me go over that. We know that in order to get precipitation, you've got to have adiabatic cooling going on, air that's being forced to rise. So we get convectional clouds that form, which can be in the late afternoon here on warm days. Areas in the tropics, that's pretty much all their rain because it's warm there all the time. We have the orographic, which we don't obviously have here in the Mid-South. And you don't really see it too much like in the Rockies, the Smokies here in Tennessee, or even the Ozarks in Arkansas, because they're not that high and you don't get that much of a situation going on. But you will see it in the Sierra Nevadas out in California. You'll see it in the Rockies and other places all around. We'll talk more about locations of that when we get into climate. What we haven't actually talked about, of course, is the cyclonic or frontal. That's what we're getting into next. That's our next deal. In your assignments on pause, your lab quiz, whichever, I don't remember what it is, 15, 16 or something like this. It's a simple quiz. It's just going to be questions based on cloud types, adiabatic cooling, and precipitation. All right, little 5 quick questions that you can probably take you about 2 minutes to answer. So that'll be the lab quiz at the end of this lecture that goes on. But what I'm getting ready to do is we're going to go ahead and go into what would have been the second lecture, and this is where we're actually we're one step closer to understanding all of the weather as all. We've got one more little variable thing to talk about. All right, so this is going to be, what we're going to talk about is air masses. All right, what is an air mass? I'm going to show you examples here, but here, okay, an air mass, it's a large body of air that may move over the Earth's surface as a distinct entity. It's very relatively homogeneous, which means it's the same in regards to temperature and humidity. Now keep in mind, you don't ever have to memorize word for word any of these definitions. You just need to have a working definition in your brain knowing what these are. Because even on the test, I'm not ever asking you to spew out an exact definition. It'll always be, if I ever give you a definition, I'll give you the definition and you just have to be able to recognize what word it is. Okay, so just make sure you understand in your head what these things are. All right. So what these air masses do, they do take on the temperature and the humidity. So we're talking about how much water vapor there is of what we call a source region. All right. And for an area to be a source region, this means that the area itself has to have a homogeneous surface, i.e. it's got to be all the same. It's got to be all land, and it's got to be all usually the same elevation of the land, all right, because then you wouldn't have the same temperatures if it was mountains. So it's got to be the same elevation, same kind of land, or all water, all right? But you can't have a mix of land and water, and you can't have a lot of elevations, okay? Because that you're not going to have homogeneous temperatures, and you're not going to have the homogeneous humidity if you've got a mix of elevations of land and in water, all right? And basically, you've also got to have time for that air mass just to sit there over a little bit of time and then pick up those temperature and humidity characteristics, all right? So the air mass itself has got to get its temp. It's got to have the, relatively speaking, the same temp, the same amount of water vapor in it, and it picks it up from, the ground area. So in your lab book, if you want to follow along, all right, this is in exercise I's where we'll be moving into for all this stuff, all right? And this is part of I1, all right? They are talking about air masses and stability, all right? And there's a little list here, and we're going to talk about this stuff right here. So if you want to write things down in your book as well, or however you guys are wanting to do this, I don't care. Okay, but I'm going to talk about these different names for air masses first, and then we'll look at the source regions. Where did I put? Where have I? There it is. Okay, so here. Okay, here are our different types of air masses. All right. It's pretty easy. We split them up, as in no surprise. I lost my pointer. Where did I put my pointer stick? There it is. All right. So, as we said, the air masses have temperature and humidity characteristics. All right. So, first off, there's two things you can be. You can be wet or dry. All right. And so the fancy names for this, all right, you think it'd make more sense if they said wet or dry, but they don't. They say continental for dry, which makes sense, right? And its little symbol is a little c. If it's wet, if it's over an ocean, all right, or a large body of water, we call it maritime, all right? That's just a synonym for meaning ocean or large body of water. And that's going to be shorthanded by a little itty bitty m. The other characteristics are temperature. And I think you can figure these out. We've got tropical, polar, and then Arctic. Okay, so tropical is going to be warmish, polar is going to be cold, and Arctic's going to be really, 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 really cold. All right, and you can combine all of these, here we go, into the different names of the air masses themselves, which are, again, based on these temperature and humidity characteristics. So you've got continental tropical air mass, which would mean that it comes from someplace warm on the land, all right? And its symbol is CT. So you need to know these symbols because, it gets a pain to write out all these long words. So be familiar with the symbols, okay, for both the test and everything like this. But continental tropical means it's a hot and dry air mass. Maritime tropical, so MT, is going to be hot and wet, right? Maritime polar is going to be cold and wet. Continental polar is going to be cold and dry. And then continental Arctic means it's really, really, really cold. That's why you have cold in all caps and bolded, and dry air. All right, so that's pretty simple. Again, you're just talking wet and dry, and hot and cold, or really, really, really cold. All right, pretty simple from that. All right, now in your lab book, right in that same section, there is a drawing of the U.S., all right, or North America, all right? So this is figure I1, all right? So I'm going to show you my worked out. We're going to actually look at the source regions. What are the areas that North America, where do our air masses form? There we go, all right? So you can copy what I have. So let me get to the right page. All right. All right, so here we go. I'm gonna hold it up here. So here we have the source regions that we find here in North America. And I'm gonna try and swing around and hold it right so you guys can see and so I can also see. Yeah. I hope nobody gets motion sick. This is not my intent by any means. All right. I need to scoot over. There we go. All right. So you start down here. We're going to start in the south. All right. Southern areas, which means it's going to be warm. That's why you see the tropicals. All right. Right here is the Gulf of Mexico. That is a source region. And the Gulf of Mexico, all right, so here's the source region right here. That's the Gulf of Mexico. This is the more, southern Atlantic, at least for the northern hemisphere, all right? We've also got the southern Pacific Ocean over here, all right? So the oceans are going to be maritime tropical, so they're going to be hot and wet. All these are going to be hot and wet, all right? We've got big ocean areas up here in the more northern Atlantic and the northern Pacific. Those are still wet, but they're going to be cold because we're farther up north here around Canada areas. And then on the land, the biggest one, of course, is Canada, right here. Continental polar that comes along. All right, a little further up here, we still have continental Arctic. Yeah, you're going, hey, wait a minute, there's still ocean up here? Yeah, but most of it's frozen a lot of the time, especially in the wintertime, so it counts as land. All right, so we're going to count that up here. This one right down here, this is our desert southwest. This is, a little bit of a continental tropical that does show up, especially in the summertime. All right, some of these are more relevant than others, especially on a seasonal basis. Now, the whole deal with these air masses, these are the source regions, okay? These are the areas where the air sits for just a little while and then picks up the temperature and humidity characteristics of these areas, be it the Gulf of I can't do this looking at the monitor, the Gulf of Mexico, or the South Atlantic, or the South Pacific, or the North Atlantic, or the North Pacific, all right, or Canada, all right, Canadian, those good old Canadians again. All right, so those are the source regions. You may notice that for the vast majority of the United States, we are not a source region, all right? So right here's Memphis, in Tennessee, in this area right here, the whole southeast, we are not a source region for air masses, all right? We've got too much of a variety of things going on, with elevations, we've got the Smoky Mountains over here, we got Ozarks over here, we got the Rockies over here, and the Sierra Nevada, and the Cascades, and all these that go on, all right? So this whole area is not a source region. Very important. Now, these air masses do tend to move. I'll explain why. That's coming up. But for now, these air masses do finally pick up and move. All right? Basically invade another area. And that's what these arrows are showing you where once an air mass picks up the characteristics of its source region, once it decides to pick up and move, where it can go. All right? So the Gulf of Mexico, that warm, wet air tends to flow up to the north, all right? Kind of where we are, actually exactly where we are, all right? The South Atlantic also tends to move on this way. It's usually pretty much trapped here along the eastern coast because the Smoky Mountains that are located right over here do tend to block those, all right? So that's going to come in that area. The maritime polar comes up here, affects the northeastern area of North America. And again, we still have the Smokies that turn into the Alleghenies and all the little mountain ranges that are up through this area. And so that, again, tends to generally be trapped just in that area. So the maritime polar from the North Atlantic does not tend to come to us. Hang on, I gotta switch hands, I'm getting. All right. And sorry, up, over. All right. The maritime polar of the North Pacific. So this area, maybe if I stand up, maybe I can do this without. All right. So here we have the Northwest. And again, we've got mountain chains all through over here, okay? If you're getting confused with these mountain chains, Google them, all right? Google a map that shows all the mountains that are here in North America, all right? Because you actually need to be familiar with those because they're very relevant to our weather that goes on. So again, these mountain ranges, so the maritime polar is usually, again, going to be trapped right here along our western coast. The same thing with this little bit of a maritime tropical here. All right. But Canada and its dry, cold air, it can swoop on down here. It can actually make it all the way down to the Gulf of Mexico. All right. And just like this warm Gulf of Mexico, wet air, it can make its way all the way up here. Because in this spot of the area, it is wide open. All the mountain ranges that we have here in North America tend to run north and south. They run this direction, which leaves this middle area wide open with zero land barriers. Remember land barriers being one of the controls of weather, all right? So CP can come down, MT can come up. And this whole area, literally, they will battle it out. And that's why this area where we are prime located is known as a battle zone. It is legit known as a battle zone, and it's this two battling air masses that we, never know which one we're going to be under the influence of, that makes our weather don't like it, just wait a minute, it's going to change. So, guess what we had this weekend? We had an influence of this cold air that came down. That's why temps got all the way back down into the 40s yesterday and today. But guess what's probably going to be coming up? Because temperature is supposed to be back up in the 70s by like Tuesday. We've got this going on. And as we're going to find out here in just a little bit, it's these battling air masses that cause our weather, and things like this, all right? Areas that don't have the battling air masses, they tend to have a bit more stable weather in the long term, as in, it's no surprise. Like this area over here, the Pacific Northwest, Washington, and Oregon, and up here in British Columbia of Canada, it's rainy all the time. Temperatures are fairly mild. It's a good chance of just light rain almost all the time. It's easily predictable. We know Southern California, especially in the summertime, it's going to be sunny and clear and sunny and clear and sunny and clear most of the time. But us, we know it's constantly changing, and it changes over the course of several hours. We never know what is going on with us, all right? And that's because we're the battle zone, all right? The Smoky Mountains and the Allegheny Mountains and everything that go up here, Adirondacks, they aren't as high, high a mountains as like the Rockies. The Rockies and the Sierra Nevada and the Cascades that we see in the western part of the country, these guys tend to be, they're really, really tall mountains and act as a really major barrier. These are much older mountains, they're much lower, and they act as they're more like a little speed hump, and sometimes the air masses can, easily go over them, especially up here in these areas, all right? But draw these in on your copy just, for you, so you have something to look at and those types of things that go on, okay? All right, so let's talk about what happens when these air masses, when they move and when they meet. So we're going to finally get into explaining our weather here within the battle zone. All right. I do want to point out, let me step over here for a second and grab my globe. All right. So again, it's not real. Yeah. Come here. All right, so there's the U.S., but the rest of the world, I'm going to back away, see if this helps a little bit. Here in the U.S., or in North America, I should say, we're the only place that has this battle zone. The rest of the world, when you look at Europe, all right, they have got the Alps that run east-west, all right? So those Alps, and they're really tall mountains too, they act as a barrier to the cold air from the north meeting up with the warmer air from the Mediterranean, all right? So they've got a border. They don't quite get, they don't have the battle zone area that we do, All right, so their weather is, they usually don't get as crazy a weather as we do. By the time you get into Asia, it's the same type of thing. There are mountain ranges all through Russia and these areas, and they all tend to run east and west. All right, of course, we've got the Himalaya, which is the tallest mountain range in the world, and the Hindu Kush, which are all found down here. So all these east-west running large mountain ranges are going to be a barrier from cold air coming from the polar regions, warmer air coming up from the tropical regions, and so they're not going to get the, quite as much of an air mass running into each other. Okay, they're going to be blocked. But lucky us in North America with this big, wide open space. Makes us very unique and makes our weather very unique, and again, constantly changing and constantly shifting. So, yay, lucky us, lucky us. So, all right. Hello there. Oh, okay, just as a quick break. She's in the room here with me. This is Corey Cat. She's 15 years old now. She's the oldest of the several cats that we have, but yeah, this is her room. So, she might pop up every now and then, and if you see her, she may be, in the background or something like that. So this is Corey Cat. She's a good girl. So I'll put her back down. She only has 3 legs. Not that it matters, but she's totally fine. She's been that way. There you go. And now you're stuck on my sweater. Whoop, hang on. There you go. That's a good girl. Okay. So if you see her, that's Corey. Okay, so where are we? All right. So we've got our air masses. You know the names. Again, there's 2 source regions for us here in the Mid-South. I guess it would help if you could see me. Those are going to be the Gulf of Mexico and Canada that come in and meet. All right, so what happens when this goes on? So I'm going to attempt to do some drawings here. The drawings that I'm going to do, there are lots of better drawings and diagrams that you can find in your textbook. There are some in your lab books as well. I'll show you a few examples of them after I draw these. So, use whatever works for you. It goes on. So give me a minute to drink something. All right, I am going to be talking about a cold air mass meeting a warm air mass. And of course, this is going to be an actual 3-dimensional occurrence. All right, it's 3D. So here is a cold air mass. Colder air we know is more dense. All right, so that's why it's being represented by this blue block that I have right here. Warmer air is less dense. All right, so here's warmer air. So when a cold air mass, think of it as just a big bubble of air that is moving across the surface, literally, kind of a big giant blob of colder air coming down from Canada. So it's going to be Canadian A. All right, and then down here in the south, all right, we have warm air. All right, the fact that it is wet is irrelevant at this point in time. All right, so we have warm air here, and it's flowing up this way. It's going this direction. Cold air is coming this way, and so they're going to meet. But because they are different densities, it's going to be, again, just like this cloth meeting up with the block. All right, this is more dense. So this is going to be forced to rise and flow over it as it continues to go this way. All right, this is the colliding air masses. This is what I'm going to try to be, drawing some diagrams of and naming different parts and words, but this is what's going on. So imagine, again, a big cold bubble moving across, 3-dimensional. It's got a front face, it's got sides, it's got a top. Same thing with the warm air mass, but this is like a brick. This is literally like a brick wall. All right, So warm air is going to be forced to rise over that, which means we're going to get adiabatic cooling. This is going to be called the frontal or cyclonic lifting, to add to the orographic lifting or the convective lifting. And then we also know, of course, we also have just if there's a low pressure center centered up above, that's going to cause lifting as well because it sucks up air. All right. But this is, again, keep in mind, this is all three-dimensional goings on. All right. Let me draw this for you. So, all right. Here, I'm going to draw the ground again. And I have a Z bubble. Oh, I don't want to do this. Here's our bubble of cold air that goes in. All right, so this is cold air. All right. And this is also, it is moving. It is advancing across the ground. It's invading the air. Then you've got warm air right here. All right, the warm air is coming this direction. And when it hits the cold air, it's forced to rise. All right? Because again, this is just like a brick wall that goes on. So these are our two air masses. This will be our CP air mass. This will be, in this case, we're saying an MT, all right, maritime tropical, that goes up. Now, where these two air masses meet, there's two terms for these, all right? There is, all right down here on the ground. So where the two meet at the ground level, this is called a front, all right? It's the battlefront. It's literally taken from, the World War I when they had the front lines of the battles, because they're talking about we got the war zone, the battle zone going on, and this is the front. This is the front line where the two warring factors meet up. That's where these terms literally came from, okay? So the front is the boundary on the ground where the two different air masses meet. But as we saw with our brick here, all right, this is actually a three-dimensional thing, all right? And so not only do we have the leading edge right down here on the ground, but we've also got the height, the top, you've got the sides. And so there's another term that is used to mean all of the boundary of this whole three-dimensional object, all right? This is known as the slope of discontinuity. It's not a short word, all right? So slope of discontinuity, all right? So that's the border of, let me close this up before it dries out. All right, that is the border going up here. It's even, up here at the top. It would be over here on the sides as well. So, if here's our cold air mass, all right, so it's the front side, it's the top, it's this side as well. All of these edges of this cold air mass, all right, that's the slope of discontinuity. And usually we'll talk about it here in the front and in the back, because you notice this bubble, again, think of it like a big gelatinous blob, even though we know it's not gelatinous, but just to help you think of it, it tends to bulge here at the front. Think of it like a slug or something crawling across. So the slope of discontinuity here in the front, the leading edge, is much steeper than the slope is back here. This is a much more gentle slope, all right? But again, so that's slope. But again, the term front, that's talking about right there on the ground. That's going to be where once the cold crosses over. If the person is, you got a person sitting right here. Woo-hoo. All right, they're in the warm air sector, but as soon as this moves in with a front, passes over it, the temperature is going to drop. It can be quite dramatically, quite quickly at times, okay? Especially depending on how steep this front slope of discontinuity is, all right? Something else I want to make clear. What makes a bubble of air cold, all right, being a cold air mass versus a warm air mass, is not based on a specific temperature. This is strictly relative, all right? So if this is 40 degrees, all right, and the warm air over here is 60 degrees, this is colder than 60. It's a cold air mass invading a warm air mass, all right? If this was 41 degrees, all right, it would still be colder air invading warmer air, all right? The cold front could be 90 degree, all right, as long as the air that it is invading is warmer, okay? So cold air mass, warm air mass, those terms are relative. Just means one is colder than the other, okay? So colder air, since it's denser, it tends to move faster than warmer air, all right? Sometimes the warmer air itself may not even necessarily be moving so much. This is just generally moving into it. So this air could actually be just sitting there. It's still going to be shoved up. Think of a bulldozer going through dirt. It's going to push up that dirt that's in front of it. That's what a cold air mass is like. And right there at the front is where it's scooping up the air that's right in front of it. So a big old giant bulldozer that comes through here, all right? Now this term front, all right? There are, I know you've heard it on weather reports all the time. The fronts are named who's doing the invading. So let me show you a picture of the different types of fronts. On maps, we have symbols for these fronts, all right? So a cold front, which means that a cold air mass is invading, is made up of triangles. And if you've got color as an availability, they'll usually make it blue, all right? If it's a warm air mass that's invading, all right, then it's going to have these, camel humps. Stupid ways to remember it. I think of, the cold front is shark teeth because they live in the water where it's usually kind of cold, maybe, all right? Whereas camels live where it's hot, often. You think of camels living in the hot areas, okay? So camel humps, whatever works, for you, all right? So here's the cold front symbol and a warm front symbol. Now, the direction that either the shark teeth or shark fins or the humps are pointing, that is an indication of the direction that the air mass is moving. Okay, so think of them as little arrows. All right? So this cold front is advancing this direction. The warm front is advancing up this way. All right? So when we go back to my drawing right here, since the cold front is the one that is advancing, all right, we draw that symbol right there. And that shows that it's pointing, see this arrow, those arrows pointing the same way. Okay, so that's a cold front that can come through. All right. Now, over here, on the back tail end of it, we might have some warm air over here again. So a warm air mass is coming this way, and it's literally going to be riding up the tail end of that cold air mass. Again, cold is denser. So this is going to be forced to rise up like this. So there's going to be a front right here where there's a difference in temperature, but this is a warm front. This is supposed to be humps. All right, and again, because it's going this direction. So the humps are pointing the same way that the air is moving. All right, so warm front, cold front. Now, some things that can sometimes happen. Sometimes, like I said, the warm air might actually literally be moving as well. It's supposed to just kind of sitting here and being bulldozed by the cold air. Sometimes the warm air is actually moving in as well. And when that happens, it's kind of like a tug of war. So if you've got the cold air moving in, the warm air meeting up with it over here, and they might not actually change position, okay, as opposed to this totally, moving in. It runs up into this, and they just kind of stay in the same spot. They stay stationary. So we can sometimes get a stationary front, which looks like this. It shows you the cold air is coming this way, the warm air is going that. So I'm going to draw these arrows in. All right. And we're at a stalemate. So the battle line, the front line, that battle line is not moving. And that really sucks. We'll see why that sucks a little later on. But if you happen to be at that location, that means the weather is not going to change. It's going to stay whatever it is with the battling going on. All right. So that's called a stationary front, when the one is not overtaking the other. Right? If one is definitely dominating the other, you just name whichever one is doing the dominating. But if it's not moving, if they're having a stalemate, it's a stationary front. Right? Now let me show you what else can happen. All right. Whoops. You can sometimes have another cold air mass that literally comes up. Call all this up. All right. And it advances through. And so you got a second cold air mass coming up, maybe moving a little faster, literally coming up on the rear end of this cold front. Okay. Of this other cold air mass. Okay. So one cold air mass coming up on the tail end of another cold air mass. And so you've got this weird situation of where you got cold air, and then warm air trapped up between them. All right, because this cold air mass displaced our warm air up to the top. And so that is when you will get what is called an occluded front, which is this one right here. Oh, I did. All right, this one right over here, where both the warm air and the cold air are moving the same direction. That's called occluded front. And that's the scenario that happens with that. All right. All right. So that's going to be, how you get changes up in temperature. But let's look at whoops. All right. I see that this is supposed to be hold on. Let me... Okay, I gotta figure out how to do this. Hang on a sec. I'll just have to go fast. All right, we'll get to it. If this runs out, I will just have 2 videos on the YouTube link. So I'll finish it when it gets to that. All right, like I told you, I don't know what I'm doing. I thought this was plugged in, but apparently it's not. All right. Now let me finish this. We've got enough to finish this. Okay, we draw the cold front and look at our warm air again. All right, so we've got lifting going on. Over here in the front of the cold air mass, all right, we have adiabatic lifting. The air is being forced to rise. And as we know, when that happens, we can get condensation. We get adiabatic cooling that goes on, and we get clouds. All right, so over here at the cold front, all right, there's a good chance we might get cumulonimbus clouds, because you notice this is a very vertical appearance. The slope of discontinuity right here is quite steep, and it runs up along to these areas. Okay, and so we can get rain. That comes out of this, but you notice it's a very narrow band of rain. All right. Now the backside, when we have a warm front, even though this is supposed to be red, but hey, we're going with what I got. All right. The warm front here, but the back edge, this is much less steep. So here, the clouds that form tend to be more spread out, right? More of a stratus type of clouds that go on, and you can still get rain out of all of these. But you notice it's going to be a much longer section of rain as it goes through, all right? So when cold fronts come through, we often have, those chance of thunderstorms that come through just before the cold front comes through. So I witnessed several times where you've had, some really bad storms that come through. Doesn't last more than about maybe 30 minutes. And then shortly thereafter, the temperature drops, sometimes considerably, depending on how cold the air is. All right. And you have that sequence of weather, all right, and that's basically what happened Friday night. We had a cold, we had a chance of severe weather. We had some rain that went through. You can still get, you can get some little lingering rain up here, but the temperatures dropped. It was much colder on Saturday. It was, went from being in the upper 60s or whatever it was to the 40s, all right. And then we've got a cold front and stuff. Warm fronts that come through where you get maybe a whole day or a couple of days of chances of rain on that end. All right. So we'll talk more about this again and again and again and again. All right. But that's your basic type of things that go on. What I'm going to do, I'm going to go ahead and end this right here. I'll get some juice on my phone so it won't run out, and then I will, I'll post them both at the same time. That'll be the continuation of this, and we'll also get into the lab work that we're going to be doing along with these air masses and fronts and all these types of things. So thanks for watching, and like I said, pick up when you're ready. Thanks.